Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 6. Student, basically in lecture number 5 we covered uh, these slides. Okay, how to calculate the dead load, live load for slab beam analysis. Okay, and then for shear analysis, okay, we calculate basically separate loading, because that loading will be used for beam analysis. So that why the a slab beam in equivalent frame method, as I explained in lecture number 1, is a different, because a slab beam is consist of both slab and beam. But when we assign movements from a slab to a beam, so in that case beam is a separate member. Okay, in that case we will use this kind of loading. Inshallah, in this lecture you will see how we will assign this loading. So we did this table in Excel. Okay, and similarly we did that one, and finally we will reach to this diagram. We explained this diagram thoroughly, that from where we got these movements, these positive movements, negative movements, how it comes. And today inshallah we will discuss this table. Okay, so this table is very important. Okay, uh, remember, once we complete this diagram basically ends the moment distribution table. Okay, because remember, equivalent frame method is a combination of so many approaches, you can say. Because at the first stage we apply the equivalent frame method procedure, which is used to just convert a 3D frame system to a 2D frame system. After converting a 3D frame to a 2D frame, the equivalent frame method procedure is finished. After that, we will use moment distribution table. By using moment distribution table, we got these movements. Now, after getting these movements, we have to use again Ddm method. Now, remember, to understand thoroughly equivalent frame method, you must know about the Ddm. Because remember, whenever we are fixing the member sizes, the slab sizes, we use all the concepts which is used in Ddm method. Okay, and the Ddm, because remember in ACI code there is a chapter 13 is totally it is a, you can say it is allocated to Ddm method and equivalent frame method, and how to determine the slab thickness and all these things. Remember, these alpha factors will be used in that cases when the slab system is supported by beams. You have beams, and I already explained these limitations. Okay, these all limitations, and in today lecture you will see how to use these limitations, because in today lecture I am not explaining these factors, alpha factors, and what does it mean. Okay, because I already explained these factors, these coefficients in Ddm method. So that why I suggesting you people that please go to my YouTube channel and open the playlist. In playlist you find Ddm method. There are 14 lectures which completely explain the whole Ddm method with examples. So here you see these methods. Okay, these 2 to 3 videos are basically I recorded, that when you have a slab system and it is a beam slab supported system, so how to use a Ddm method. So if you watch these 4 lectures, because in this lecture 1 and 2 I explain those factors, how to determine the thickness for a flat slab system or when you have beams. Okay, and these methods, these videos basically is allocated to I explain basically mm, the Ddm method when you have a beam slab supported system. And similarly, the rest of the videos explain the design procedure, how to once you got your movements, how to distribute that movements into your column strip and your middle strip. Okay, so today in further lecture I will not explain those things which I have already explained in these videos. So please watch these 14 videos for the rest of the videos. Clear? So what we have further, we have, okay, where is this one? Now you see, we have basically spans. We have exterior panel and we have interior panel. Clear? Here you see in this diagram, you see we have exterior panel, we have interior panel, and we have again exterior panel. Clear? Now in exterior panel, what we have basically, you see we have exterior negative movement, then we have positive movement, and then we have again negative movement. Remember, this is our exterior support. Okay, this is our first interior support, and so on. Clear? So here we have basically a negative moment. Okay, as you see here in this diagram, in the top story, you see we have a negative moment. So E negative, this one is E negative. Clear? Then we have a positive 67. This one will be positive. Okay, this one will be denoted by, in our table, denoted by E negative. Clear? And this one will be denoted by I negative. So this is interior one, and again it will be repeated for the rest of the moments. Clear? So that why you people see here that E negative, positive, I negative, negative, positive, negative for interior panel. Okay, so let me open my notes. Where are those notes? Okay, here we have okay, we finished this one. Clear? And already we finished this one, and now we have this one. Clear? So what we have further, distribution of moments laterally. Clear? So remember this point, these points are very important to understand. The moment which are calculated up to this point is now distributed to column and middle strip by using direct design method procedure. Okay, so here you see the moments. Okay, now these moments are basically the longitudinal moments. In Ddm method, if you have a concept, okay, about a Ddm method, in Ddm method basically what we did, we basically find out we find out m naught, that is the static moment, and then we distribute that static moment longitudinally, okay, by 0.65 and 0.35 coefficients. Okay, we use those coefficients, and what we did basically, let me show you. Okay, once we, okay, let's say we have m naught. Okay, we have m naught, and once we calculate that m naught, we distribute that m naught, okay, longitudinally by multiplying it with some coefficients, okay, in this pattern. Clear? Now after m naught is you can say it is distributed in longitudinal direction, then we distribute those longitudinal movements in lateral direction. Okay, we distribute those longitudinal movements in lateral direction. You see in the Ddm method basically we have a column strip. Let me show you here. Okay, so what we have basically, we have some column strip and middle strip, half middle strip, half middle strip. So the longitudinal movement which we have here, let's say, okay, so some part 100% will be absorbed in this point, while I think so 75%, round about 60%, let me check it. Here we have in interior negative factor movement positive, and again this one. Okay, so round about 52%, I think so, 52% without H beam, sorry, slab with beams Okay, exterior edge unrestrained. Yes, if you have exterior, there is no beam. Okay, so 0% will go to the middle strips. Okay, so all those these limitations, these coefficient is used to laterally distribute the moments. Clear? I'm not explaining those things, okay, because I already explained in those lectures. So please go and watch those lectures. So what I mean, you have to understand that the movements is have to distribute it in the lateral direction. Now, remember in equivalent frame method, we directly obtain these longitudinal movements as you see here. These movements, okay, these are the longitudinal movements now. So what I mean to say here in these notes you see here, no need to use longitudinal distribution coefficients, means 0.35 and 0.65. You don't need to use those coefficients because the moments which we got is longitudinally distributed. Here we just need lateral distribution factors, clear, coefficients. This should be clear. We don't need to use 65% and 35%. We just need to distribute these are the longitudinal movements basically. We just need to distribute these movements in the lateral direction. Clear? This is basically what I have mean. Okay. Now the coefficient can be interpolated from chart or graph A4 available in the appendix of Nielsen book. Now we have to use those coefficient. Remember the coefficient which we basically used in Ddm method are these coefficients with different conditions. Now these coefficients could not be used here now because these coefficients are not for the beam slab supported system. We have to interpolate these coefficients now from graph A4. Now how to interpolate those values and what are those graphs? So these are the graphs, these are the tables, okay, which I already explained. If you watch these videos, here you see in these videos I already explained thoroughly those videos, okay, those graphs and those tables, okay, in this video and this video. So you will understand how to use those tables, okay, and what does it beta means and what does it alpha means, okay, and here you see what is beta and what is C. I already explained this term C, which is a torsional constant, okay, so it will also further help you. So in Nielsen book you will also find at the end of appendix, okay, or Nielsen, at the end of the Nielsen book you will find these tables as well as, okay. Now what we have next, okay, we have to use graph F4 and from that graph F4 we will find those coefficients. Remember we cannot use the Ddm method coefficients, okay, we have to obtain the coefficient from graph F4. Now grafting the lateral coefficient, but we need alpha and beta because there are beams, okay, I already explained it. Now we need L2, that is already we know it, okay, and we need L2 by L1 ratio, longer to shorter span ratio, clear. And in this case, in our example, as we know L2 is 20 and L1 is 25, so L2 by L1 ratio is 0.8 for east-west direction, and for north-south direction L2 by L1 will be 1.25. This is very, very important. This ratio is very, very important. Clear? Then alpha F factor is what? Modulus the elasticity of beam to the moment of inertia of beam divided by modulus elasticity of steel to the moment of inertia of slab. We already calculated these values. So remember what this condition means. Remember these values will be only used when this condition is fulfilled, okay. I already explained this in these lectures, okay. Now ECB is equal to ECS, so that's why L5 equals to IB divided by IS, and I already shared this section, okay, with you people, and you can also check this by my YouTube channel. Now next what we have, for edge and interior frame, the lateral and transverse beam movement, okay, moment of inertia will be calculated as multiple of rectangular I beam. This is very important. This is very important for L and T beam. Okay. Now, how to calculate moment of inertia, okay, for L and T beam? IB is already calculated, that is for beam 14 by 20 inch cross section we have beams, so this is IB. Now for edge beam, IE, that is for L beam, okay, the beam which is running along the let me show you that picture, not this one, yes, this one, okay. So the beam which is running along here, this is L beam, and the beam which is running along this line, this is T beam, transverse T beam. Now to calculate the moment of inertia of this L beam and this T beam, we will use multiple. Here you see, this is basically ACI code criteria, multiple of rectangular I beam. Now this basically make easy your calculation. We have IT is 18700 and IE is 14,000 inch ki power 4. Here you see IE will be 1.5 times of this moment of inertia, and IT, moment of inertia of T section, will be 2 times of IB. Clear? This condition is also explained in Nelson book. Now I is moment of inertia of slab, we already calculated this, okay, and alpha F factor. Now I already explained this, what is alpha F factor. So this is moment of inertia of the T section divided by the moment of inertia of slab, okay. So I already explained it, and here you can also see here what is alpha factor, okay, what is alpha factor, not this one, where it is, this one, alpha. So ECB ECS is constant, IB divided by IS, okay. So where we are here, now we calculated our alpha F is 2.7 for interior east-west frame, remember, okay. Alpha F 14 divided by, okay, this is 3.11 for exterior edge east-west frame. Remember, we have two frames, okay. If you watch this video, you see here we have two frames, that is exterior equivalent frame in east-west direction, but that is the exterior equivalent frame, and we have interior equivalent frame that is also in east-west direction. So for that, your alpha F will be different. For this frame, your alpha F will be different, okay. So you must take care of these differences, okay. So next we have to multiply this alpha F with L2 by L1 ratio, okay. We already calculated L2 by L1, so we have 3.375 for north-south direction. Remember, if somebody is calculating this alpha into L2 by L1 factor, so in north-south direction, okay, you have this one, okay, you have 3.375. But in our case, which is in our case, we will use 0.8 times 2.7. L2 by 1 is 0.8 and alpha F is 2.7, so 2.16. remember, it is more than 1. It must, if it is less than 1, so there are charts, there are tables, you will see why we need, okay, we have to compare this with 1, whether it is greater than 1, whether it is less than 1, okay. So it should be remembered. I will explain this, okay. Next, now we need beta T. So beta T is what? It is equals to ECB into C divided by 2 ECS into IC. I already explained this here. Where is ECB? Okay, that is the beta, sorry. So here you see beta is ECB into times C divided by 2. We already calculated C, ECB and EC is constant, so simply beta T equals to C divided by 2 times IS. C is calculated for T section, already we did it, and for L section or for H beam we already calculated this one, and IS is also already calculated. So basically we have all things are readily available, so that's why you see here C 12694 divided by 2 times of IS. IS is 6 at 60, so we got 0.93 from table 13.2 or graph F4 Nelson interpolation from table. Now this C value is remember we have to use this C value for we have H beam as well as we have T beam. Okay, now we have to use graph A4. Now where is graph A4? Okay, remember in those lecture, if you watch these videos, I thoroughly explain these concepts. Okay, you see this lecture. So in this lecture, basically at the end of this lecture, this method is basically start over here. You see here these coefficients, okay, the Ddm method coefficients, okay, and these tables. You see now these are the tables when you have a slab with beams. Okay, remember these coefficients is only used when you have when you don't have any slab beams. Clear? So once you have beams, you have to use these tables and you have to interpolate your values. So here you see we need L2 by L1 ratio, and here you see our value is more than 1. Alpha, we already calculated this ratio and we see that is 2.16, which is more than 1. So if it is equals to 1 or if it is greater than 1, we have to choose these values. Now if it is less than 1 and greater than 0, so we have to interpolate in between these values 75 and 90. Okay, so we have to use this table as well. This is basically, and we have to use this table. So here we will use beta T value and here we will use alpha factor. Clear? So we have to use as well this table. Okay, and the rest of, I think I already explained these concepts in these lectures, so please go there and watch those videos. Clear? So okay, now this is graph A4. Remember, you can use either this graph or either you can use these tables. Okay, so these tables, here you see positive factored moment. This table will be used to find the coefficient that will distribute the positive moment in lateral direction. And this table, you see exterior negative moment. This means that if you are distributing the, where it is, this one, if you are distributing this negative exterior moment in this direction and in this direction, so the coefficient can be found by using this table. Okay, and if you are going to distribute the interior negative moment, this means that if you are distributing this moment, that is okay 1 1, so you need to use this table. Okay, so for each moment, this is for interior negative moment, this is for exterior negative moment, and this one is for positive moment. Clear? And if somebody using this chart, so in this chart you see in this upper chart will be used for interior negative moment, this middle one will be used for exterior negative moment, and this lower one will be used for positive moment. So how to use this chart? Let me explain this chart. Okay, here we have. Okay, so as you see that in this how to use this graph basically. Okay, we have a ratio of L2 by L1 is 0.8. We already see this ratio. Okay, we already see this ratio. Now where is this ratio? Okay, here we have L2 by L1, that is in our case 0.8 for east-west direction for interior frame. Okay, for interior frame this is 0.8. Okay, now so here we have 0.8. I already marked that point, okay, because it starts from 0.5, then 0.6, 0.7 and 0.8. So this red line is basically denoting 0.8. Now if you are picking your positive moment, okay, let's say we are picking your positive moment coefficient. So here we have these inclined lines. These inclined lines basically is denoting alpha 1 L2 by L1 ratio. So we already calculate this ratio as here we see where it is, this one, okay, this one, alpha f L2 by L1, this one, okay, not north south direction, we have this case. So this is 2.16 which is greater than 1. So this suggests that this, where it is, this one. Now here you see the upper line, the upper inclined line, basically it will be used in that case when your this ratio alpha L2 by L1 is greater than 1. So we will use this line. So the line, this perpendicular line touches this inclined line at a point. So we pick that point here and we draw a line straight, a straight horizontal line, and we find out the point where it touches this line. Okay, so here you see this is a little bit higher than 80. So this means that our value is 0.8 or 0.81, which is close to 0.81. Clear? So this is first coefficient for positive movement coefficient. Okay, now the next coefficient is exterior negative moment. Okay, exterior negative moment. For that, you see here, this is a little bit tricky. Okay, this is a little bit tricky. You see the line which touches these inclined lines, same as here, and then we have to proceed that line in this direction. Then we have to find the point where it touches these inclined lines. So here it touches, okay, and then we have to go in upward direction, okay, but parallel to these lines. You see here, parallel to these lines. Then we have to find out our beta t. So as in our case, beta t is 0.93. I already calculated that beta t here. Okay, that is 0.93. So here we have 0, 0.5, 1, and it's very close here. 0.93 is around about here. Okay, so we have to draw a line here. Okay, and we will find out that point where this upward line and that line, okay, that line, this one, at which point they crossing each other. So this is the point at which basically these two lines, this upward line and this inclined line, touching each other. So after getting that point, we have to draw a horizontal line in this direction. Okay, and we have to find out the point where it touches this vertical line. So you see this blue line, okay, and this is our required point. Clear? So 80 and 100, so there is 90, round about 92, 93. Remember, this depends, there will be a little bit difference. Somebody may take it 0.92, 0.91, 0.93, okay, which is very close. Now this is the coefficient which will be used for exterior negative movement. For which movement? Okay, let me show you here. For this movement we will use the coefficient 0.93. and for this moment, which is the positive moment, we will use the coefficient 0.81, and for this one we will use 0.9193. Clear? And next, for this interior movement, we will follow the same procedure. Here we come to this chart, and here we see that the line which is going upward direction touches that inclined line at that point, and we have to draw a horizontal line, and we will pick the point which is the same 0.81 as here. Okay, so this is the way that how you have to find out these coefficients. Clear? I already explained here. Okay, now we will coming back to this chart. Okay, the chart you see here, and you see these coefficients. Clear? These coefficients 0.93, 0.81 or 0.8. I already explained. Somebody may take it 0.81, someone may take it 0.8. Okay, so it doesn't matter. Clear? Now you see these movements. These movements is from your movement distribution table. Clear? This is basically for top story, remember. Now from top story you have to just pick these point 34, 67, 111. Okay, only the maximum one, and then this 42. So you have to just show those movements right here. Okay, for E negative, positive. Okay, and then remember this 93, this is basically 93%. What does it mean? This means that this is very important point. You must understand this point. Clear? You must understand this point. Remember, once you have interior equivalent frame, this interior equivalent frame, we divide the slab into two parts. Okay, in column strip and half middle strip. Now, as you already know that we have beams, okay, right here. Okay, we have beams right here which is running in the north-south direction. Clear? Let me show you those beams. Okay, so you see here we have beams which is running in this direction. Now it is very important to understand this point. Remember, as we are analyzing the slab beam, so we have to find out the moment. Basically 93% means that you see here 93%. Okay, this 93, this means that you the total movement that is 34, its 93% movement will be remain in the column strip. Okay, in the column strip. Remember, in this column strip 93% movement will be absorbed. 93% of 34 will be absorbed here, while the rest of the 7%, 100 minus 93 give you 7%. That 7% movement of the 34 will go to that middle strip and this middle strip. Mean that if you take 7% of 34, it will give you 5. Now that 5, half of that 5 movement will going toward in that half middle strip, and 2.5 something, okay, will come here, and the rest of the 93% movement will be absorbed in this column strip. Now it is very important that now you see here in the column strip. Okay, in the column strip it is very important to understand. Okay, it is very, very important, because nobody will understand this thoroughly. Clear? So that's why I'm basically forcing this point that you must understand it. Okay, remember we have change my pen. Okay, this is column strip. Clear? This is column strip. Now as in a column strip, we see we have beam and we have slab. This is very important. Okay, Now the 93% movement, let's say 0.93 of 34, okay, of 34. Now it will give us how much? It will give us, let me calculate it, 0.93 times 34, it will give me 31.62 cubic feet. Now this much of movement will be now here, okay. So as we have slab and as we have beam, so what portion of movement will be taken by this beam and what portion of movement will be taken by this slab? So ACI code basically explained that 85%, okay, 85% of this movement, this 31.62 will be taken by this beam, while the rest of 15% will be taken by this slab. Clear? This is very important. So that's why basically they multiply 0.15 and 0.85. This means that basically they take what they did here, they multiply 9.93 with this 34, then again they multiply 0.15 with the product of these two, they got 5. So this 5 movement is basically absorbed in your slab, okay, in your slab. It will be taken by your slab, and the rest of the movement, that is 27, is taken by the beam. So the beam at this point, let's say if this is the beam, okay, so in the beam there will be, okay, 27 movement, okay, feet movement. This is very, very important, okay. Now the rest of the 2.38, it will be good to the half step and half middle step and half. I already explained this. Similarly, repeat the same procedure for all the movements, but here for the exterior it is 0.93, but here we have 0.8, and the rest of the calculation is same. Clear? But the only point which I thoroughly explain is only this point, that you must understand what does 0.15 means and 0.85 means. Okay. Now the rest of the procedure is simple. Clear? Once, remember, we will not design the slab for these movements. Remember, this is the slab beam movements. These are not the slab movements, these are not the beam movements. These movements are combined for the slab beam. We have to distribute these movements into the slab and into the beam by multiplying these movements with these coefficients. Okay, after multiplying these coefficients, these are now the net movements, okay, are the, you can say, the movements for which we have to design our slab and our beam. These are, we have to design the movement, flexure design will be done for these movements, beams, okay, and the column strip will be designed for these movements, and the middle strip will be designed for these movements. So how to design and how to assign these movements, again I have thoroughly explained this procedure, how to design. Okay, here you see in these videos how to show those movements and how to combine these movements. Now you have to watch these videos, okay, because I'm not going to explain the rest of the procedures. Clear? I will explain now the procedure for beam. Okay, so you see here 27, 75, 71, 58, these movements from where chosen, these are these movements. Okay, at their locations they show the movements. Okay, let me show you my notes here. So here we have. Now this is very, very important, because I'm somebody must have knowledge about the tables. Okay, I already explained the procedures from graph. Okay, no, here I basically explain the tables. If somebody unable to use the graph, and if these tables are available, okay, so you can also use these tables and you will find the same coefficients. okay, as those you got from your graph. So here you see, let me use to show you how to use these tables. Okay, I already explained this, but you see here we have alpha f1 L2 by L1. We already calculated this factor. This is 2.16. Okay, and L2 by L1 is 0.8. So 0.8, you see 0.5 and 1. I choose this table from ACI code. Okay, here you have, I think so, this one. Clear? This will be used for interior negative moment. Clear? So you see L2 by L1 ratio is 0.8. Now 0.8 exists in between 0.5 and 1. Clear? And our alpha, this value is as 2.16, which is more than 1. So we have to use these coefficients. Now, okay, so we will use 1. Clear? 0.9, 0.75, I think so. 0.5, okay. 0.5, 75 or 0.75. Okay, this is all right, it is okay. Now you have to interpolate the value, okay, which is correspond to 0.8. So you have to use the interpolation formula, and you got your coefficient, that is 0.81. Okay, this is the interpolation formula. Okay, I already explained this interpolation formula. Okay, now the same value is obtained from graph F4, as you already see. Now this 0.81 is interior negative moment coefficient. Okay, because this table is used for, you see here, which is written here clearly, you see here, this is for what? This is for interior negative moment. Now for exterior negative moment, that is E negative, you have to use this table. So let's see how to use this table. Now similarly, from same table on our graph F4, the lateral positive moment coefficient will be 0.81. okay, for that purpose you have to use remember, you have to use this table, this one. Okay, positive factored moment. Okay, you have to use this one. But for interior negative moment, okay, exterior negative moment, sorry, E negative, that is 0.93. basically we from graph F4 we got 0.93. now how to use this one? Okay, so you have to, first of all, you have to find your beta t value. Already we calculated that beta t is 0.93. now this is very important, and our alpha factored value, this value is more than, so we have to use these two lower table, this one. Clear? So as our beta t value is less than 2.5, so we have to interpolate in between 0 and 2.5. this is very important. We need to do interpolation, because our L2 by L1 ratio lies in between 1 and 0.5, that is 0.8, and similar. So we need two interpolation. I did this calculation here. You see here, look, our beta t is 0.93. So beta t lies in between 0 and 2.5. Already explained it. We need two-way interpolation in table 13.2. Okay, now because our alpha L2 by L1 is 2.16, which is more than 1. So here we need two-way interpolation. I choose these values from that table, and you see the way interpolation. See, we have to first of all calculate this value, then we need to find out this value, and then by using these two values we will find this value correspond to 0.8 and 0.9 or 0.93. so all the formulas are here, how I got this value, how I got this value, and how I got this final value, that is 93% or 0.93, and I already obtained this 0.93 from graph F4. So this is very important to understand. Therefore I write down all these things to understand, because I see so many students unable to use these tables, how to use interpolations, how to use graph. So students basically they're facing troubles, okay, to use these values. Now the rest of the procedure is simple, okay. The rest of the procedure here, you see what we have to do next. Okay, we have to assign, okay, after calculating these movements, we have to assign those movements to our beams. Okay, this is our beam now. Remember, now this is our final beam, and this is basically our beam. Okay, top story beam, remember. And now we have to assign that 1.24 kip per feet loading, not 1.75 kip per feet loading, remember, because 1.75 kip 575 kip per feet movement is for slab beam. Now here we don't have slab beam, we have just only beam. So that's why we are assigning 1.24. Okay, and these are the movements. Now these are the beam movements, these are not the movements of slab beam, because we find out these movements by using these coefficients. Okay, so finally we have to do the same procedure as I explained in lecture number 5. So follow that procedure, find out these reactions, your net reactions, and draw your shear force diagram. Okay, and one thing more which is very important, you have to find out your fast movements, fast shear and fast movement. Remember the movement which we got here, 27 and 13.74, similarly 16 shear and 17.26, these are the line movements, or you can say these are the center line movements. ACI code, if you visit the ACI code permit you to use the fast movements. Now what are the fast movements? This is very important to understand. Clear? So where are those fast movements? Let me show you those fast movements. Okay, you see here, this section basically explains negative factor movement shall be located at face of rectangular supports. Circular or regular polygon shaped support shall be treated as square supports with the same area. This means that you ACI code allow you to use fast movements, not the center line movements, because remember it is very important to understand this difference. Because let's say if you have a 4 feet column right over here and a 4 feet column right over here, so the center to center distance will be more. Okay, it will be more, and that create more movement as compared to the fast movement. The fast movement will be lesser as compared to the center movement. So this is basically make your design economical. Okay, so that why you see this point here, you see this point here. Okay, so you have to find out these fast movement. Now how to find this fast movement? You have to draw the shear force diagram first for the center line movements. Then you have to find out this distance. This distance will be how much? You already know that the size of your column is 14 inch, so this distance is 7 inch. Now once you got this 7 inch, by using the similar triangular rule, you will find this shear as we did for the shear analysis. Similarly this point, this shear, similarly this shear. After that you will find out this shear area. Okay, this shear area will be 13.74 plus 13 divided by 2 times this 7 inch. You have to multiply this 7. You got the shear area. You just need to subtract the shear area from this 27. You got this 19.2. Similarly here, this 65 will be equals to this 75 minus this shear area. You have to find out this shear area. Okay, and you have to subtract that shear area from this 75. You got this one. Let me show you this calculation in my Excel sheet. I think so I did it in my Excel sheet. Okay, here we have in this sheet for top story, okay, dead loaded top story, okay, and this one. So you see here, this is the calculation, okay, this is 27. See, this 27 is from my other sheet, which is multiplied with those coefficients. See these coefficients, okay, this is basically 34 times that coefficient 0.93 and that coefficient 0.85. Clear? Now uh, that 34 is multiplied with this, with the product of those coefficients, these two coefficients, and we got this 27. Clear? Similarly, this one is that is 111 for top story. I think so. This is for top story. Yes, this is for top story. Now let me maximize this. Okay, now this 76 is basically 1 already I explained it. Okay, here we have this one 111. Clear? Now that 1 okay, it should be multiplied by these, the product of these two coefficient, okay, to get the beam moment. Clear? Similarly, this one you see here, you see here, similarly you see here, and this one, and this one is again 0.93. Clear? After getting these moments, you have to find out your net reactions, as I already explained in this whole procedure in my lecture number 5. And finally you will got these positive moments. Now these are the maximum positive moment. Remember, maximum positive moments for your beam, remember. Okay, and I think so it is calculated right here. You see 46, I have got 45, and here I have 28, and here you see 29. Okay, so this is a little bit difference, doesn't matter. Okay, no, for this 46 and this 29 you have to find out steel for this beam. Okay, but remember, this is remember we have to include, this is only for dead load. Remember, it must be remember, it is only for dead load. We have to include, and next we have to include live load. After assigning live load and multiplied these moments with the factors, that is 1.2 and 1.6, after that we will find, okay, I will explain the whole procedure in my coming lectures. Okay, but I just give you the idea that if you are designing this beam for only dead loads, so you have to design for this 46. You got this 46. Now you have to multiply this with 1.2 factor to factor it. Okay, or 1.4. Similarly, you have to multiply this 19.2 with. Okay, so next you see 45, 28, 28, 45. Now let me show you this table. Clear? This is very important to understand it. Clear? Now in this table you see here, let me minimize this. Clear? In this table you see here that what we have basically, you see at a distance 0, which is this moment. Now I choose this moment, that is minus 26.61 67, that is 27. Now this is the center line bending moment. I have to find out the critical moment, or the fast moment. Critical moment means the fast bending moment. Now you see 18.99 are just 90. So how I got it? I use this whole formula. But the simple way is, you have to find out this shear area. Okay, or either you can use, okay, this 27 minus this reactions time this 7-inch distance minus plus minus, okay, minus 1.24 times that distance divided by 2. Okay, as the usual way we did it. Okay, so you see here that reaction, that moment, okay, and that reactions time distance okay, minus this is the UDL loading, okay, and a half. So this is the whole formula which I basically use in my Excel sheet, and I got that fast moment. So here you see the fast moment is 19.2, which is close to, if you calculate the shear area and subtract from 27, it will give you 19.2. If you are using that procedure which I already explained it, so you will get 18.99 around about 19. Okay, so it doesn't matter. Now this 65, so 75 minus that shear area, or either you can see here positive movement. Remember, the positive movement should not be, that will be remain same. Okay, so you have to just convert the center line movement into fast movement, not the positive one. Okay, so 66, I got 66, and here it have 65, which is closed. Okay, so if you find this shear area subtracted from 75, you got 65. But if you are using that procedure which I explained it, okay, which is the normal procedure you see here in this formula, so you got 66. So already it is closed. Similarly, all these moments, okay, these are the fast moments. Now the next is the shear values. Okay, I choose those shear values from here, and then I convert those shear values to the critical shear force. Okay, these are the critical shear force, or you can say these are the shear force at face. Clear? So I already explained these procedures. Okay, you just need to this shear minus you have load times the distance. Okay, so here we have this one also. Okay, shear, as already shear is negative, so shear plus, if you add plus sign here, so it will be negative, this one will become negative. Clear? So shear minus loading, UDL loading. Okay, so I mean to share you this calculation, basically, that if you done this calculation Excel sheet, it will be a more easy for you, because manually it is very difficult. Clear? So this is the procedure how they got these movements. Clear? From where this 2046 comes, okay, and where this 65 comes. Remember ACF, you here you see ACA code. So ACA code basically explain that if you have this circular type of column, if you have a polygon type of column, if you have a column which is not assigned in your longitudinal and your analysis direction, which exists in this shape, so you have to rotate this, and you have to consider this as a square shape. But if you have a polygon shape, so you have to convert that polygon into a square shape, okay, by just multiplying this height with 0.93. If you have a circular column, so you have to convert this into a square column by just multiplying the diameter of that circle with 0.89. And as in our case, this is 14 by 14 inch column, so if the value which you got here, let's say 10 inch, so that 10, this distance will be now 5 inch. In our case, it is 7 inch. Clear? And if you, let's say, for example, if you have a wall section, this is also very important. If you have a wall section, so what then what you will do? Okay, you see here, if you have a circle, so you have to find out the face moment. Okay, this is very important. Okay, many students confused in these diagrams. Okay, so you have to find out the face of your column. So in this circular shape column, what will be your face? So this one will be your face. Similarly, in this shape, this one will be your face, and this means basically you have to convert these shapes into your square shapes. Let's say if you have a column capital, now your face will be located at a distance of a by 2. A is this much distance, so this will now will be your face of the column. Similarly, let's say you have a column, you have a wall, okay, and this wall is more than C1. You can see C1 is greater than 0.35 times of L1. L1 is the center to center distance. Now you have to your face will be located, remember, this line should be extended right here, but it should not be more than 0.175 L1. Okay, this is very important. So you have to find out 0.175 L1 and then your this distance, that is 7 inch. So 7 inches, if it's 7 inches less than this one, so okay, you will use 7 inch, but if 7 inch is greater than this value, then you have to use this one. Clear? This is very important and many students will confuse in this point. Clear? So it basically makes your design economical, okay, because the center line movements are greater movements. Clear? So this is just only for top story. You have to do the same calculation in this table. You see here they tag for this is for interior story. Okay, so for interior story the movements are different, the coefficients are same. Remember, the coefficients are same, and you have to find out your beam slab movements, your beam movements, your column strip movements, and your member strip movements. I also did the same calculation. Okay, let me share you this one. Okay, so you see 35, 74, 69, 59. I already share you this one. This is 36, and here we have in my table it is 35. So here I have where it is 44. This is positive moment. So I have 42. Okay, I have 42. Then I have 74, and here it is 74, 69. I also have 69, 69. Clear? And here I have 29. This is positive moment, and here you see this is 29. So this one is closed. So next one is 59. I also 59. So this is the procedure. Okay, if you you've done your calculation Excel sheet, you can easily get the things as you see here. And then again you have to convert, these are your center line movements, and you have to convert your movements into face movements. Clear? Into your face movements or into your critical moment. Clear? So this is basically for what? For your interior story. You see here interior story for dead load moment, and this one is for your top story. Clear? So after this you have to do the same calculation. You have to find out your fast movements. Here you see 44, I have 42, 29, I have also 29, and here you see 69, I have also 69, this 59, I have also 59. Okay, and then you have to find out your fast movements. So here it has 28, and here I have basically this is center line movement, and where it is, yes, I have 18, that is 19 roundabout. This is for here we have, so I have 28. Okay, and here they have 28. Okay, so here it has 64, and I have this one 64. Clear? So this is the critical. Let me check the shear. So the face shear is 13.23, and here it has 13.27. Here 16.27, I have 16.33. Clear? So these are close. Okay, and these results will be accepted. So this ends up, yeah, this ends up your interior top story and your interior story and your top story. Okay, this basically these are the results for dead load. Remember, it is very important. We did the analysis for dead load. Clear? And we assign this load, and now the rest of the calculation will be for live load. And you see this live load 2.88, and for shear we will use this live load will be 1.73. Okay, so that we will use the concept of pattern loading, okay, which I will explain inshallah in my next videos. But before that, uh, before going towards the live load or pattern loading, we have to assign now the loadings to the columns, okay, by using these distribution factors, and we have to find out the column moments. So inshallah in next lecture, like that is lecture number 7, we will cover that portion, how to find out the column moments, okay, and how to assign them into upper and bottom story. Thank you for watching. See you in next lecture.